We reverse engineer the load profile section of Oracle AWR report. This script produces the exact same output you see in AWR report. You can download the script from the PowerPoint. There are 32.7 logons per second, but right below that, the user logons column shows 0. So that raises a question. Where are these logons coming from, and what are they doing? The load profile section gives you a quick overview of the database workload. I've developed a SQL script that can generate the same results as the load file's output. This isn't illegal reverse engineering. It's simply an effort to understand how Oracle calculates these numbers. After all, you can't mess with a big tech company like Oracle, and it's certainly not worth going to jail for. In fact, I've almost reverse engineered the entire report, and I'll be sharing more examples as we go along. As we have understood how Oracle computes these metrics, we can create a table to describe where these metrics come from. This table maps each node profile metric to its corresponding Oracle view and source statistic. The leftmost columns list metric names featured in the load profile. The mid columns specify the view from which the relevant metric is retrieved, and the rightmost columns specify the source statistics used for calculation. Among all load profile metrics, DB time per second is arguably the most important. Here is 39.2. It's the first thing that I habitually check when I'm given a new AWR report. This value tells you how much workload your database is actually handling. It's derived by dividing DB time by elapsed time. Here gives 39.2. This can be interpreted as an average of 39.2 fully busy sessions, or 78.4 half-busy sessions per second. When we talk about database applications, we usually split them into two main types, OLTP and OLAP. These two are classical examples of load profiles. OLTP on the left, OLAP on the right. OLTP stands for Online Transaction Processing. These applications deal with a large number of short, real-time transactions, things like banking or e-commerce, where every click or payment has to be processed right away. OLAP, on the other hand, stands for Online Analytical Processing. These applications are designed for heavy analytical work, running complex queries on large amounts of historical data. For example, business intelligence dashboards or company reports. Now, the differences between these two workloads show up very clearly in the AWR load profile section. Let's look at the first column, logons. In the OLTP profile, the number of logons per second is 0. On the OLAP profile, it's about 32.7 per second, which is surprisingly high. Right below that, the user logons column is also 0. That tells us those 32.7 logons aren't from users, but from background processes. And that makes sense, because OLAP applications often spawn actual background sessions to parallelize complex queries. By contrast, OLTP applications don't really need parallelism. Their queries are short and simple, so background logons stay at 0. Another difference is that OLAP applications usually use up more CPU than OLTP, because they are running heavy operations like sorting, joins, and aggregations. Transactions are also quite different between the two. OLTP applications handle a much higher number of transactions per second, but each one is usually small and simple. In contrast, OLAP applications deal with far fewer transactions, yet each one is much larger and more complex. That's why, on a per transaction basis, OLAP tends to be heavier in resource usage, reflecting the complexity of analytical queries. Metrics like block changes and redo size, which measure how much data is being modified, is usually much higher in OLTP workloads. That's because OLTP applications are constantly inserting, updating, and deleting data. OLAP applications, on the other hand, hardly ever change the data. They mostly just read it, so those numbers stay pretty low. When it comes to I/O patterns, OLTP applications are usually write-heavy, with lots of updates and inserts happening all the time. OLAP applications are the opposite. They are mostly read-heavy, doing big scans and aggregations across historical data. Another difference is in SQL work area usage. OLAP applications tend to use a lot more of it than OLTP, because they are running heavy operations like sorting and hash join. A user call is a request from the application to the Oracle database kernel to do something, like login, parsing, fetch, or execute. It's a good way to measure how chatty the application is with the database. Now, here's the strange thing in this OLTP application. For our passes plus executes is around 43,000 per second. But the user calls are just 6.5 thousand per second. A reasonable guess is that the application is calling many PL/SQL procedures. Each single call to a PL/SQL procedure can trigger a lot of passes, executes, and fetches behind the scene. You can back this up by looking at recursive calls in the instance activity states section. It's showing more than 42,000 recursive calls per second. And if you check the SQL statistics section, it says that the captured PL/SQL accounts for 96.9% of the total DB time. So it's pretty clear that most of the SQL executions are executing inside PL/SQL procedures. This explains why execute plus pass way greater than user calls. The oddity in these OLAP applications is that we see 136 passes and 226 executes per second. but user calls are way higher, 4,133 per second. So where did the actual 3,771 calls come from? In OLAP applications, result sets are usually much larger than in OLTP. Each execution can return so many rows that they exceed the array size, which forces Oracle to fetch repeatedly to deliver the full result set. So those 3,771 missing calls may be fetch calls. You can back this up by looking at the secret round trips to from client in the instance activity states section. It's 3,968 per second. Oracle OCI library bounds operations like a close cursor, pass, execute, and fetch into single round trip. So this number won't match perfectly. Still, it's a solid approximation. In this case, those extra calls amount to 3,771 fetches, or roughly 17 fetches per execute.